This is week 4, entropy rates of stochastic process. Lecture notes in the information theory. I'm Hikmet Kamberay, a professor at the Faculty of Engineering, International Balkan University. The outline of the lecture for today includes Markov change, entropy rate, second law of thermodynamics. First, I'll talk about the Markov change. Initially, I'll define a stationary stochastic process. A stochastic process, it is denoted as xi, which is an index sequence of random variables. In general, there is an arbitrary dependence among the random variables. The joint property mass function is given as the following. P of x1, x2, xn, it is equal to the probability that x1 takes the value little x1, x2 takes the value x2, and so on, xn takes the value xn. Where now the tuple and tuple x1, x2, xn, it is a sequence from the alphabet set chi n, for n equal to 1, 2, and so on. By definition, a stochastic process is called stationary if the joint distribution of any subset of the sequence of random variables is invariant with respect to the shifts in the time index. So this would mean that the property of x1 being equal to x1, x2 being equal to x2, and so on, xn being equal to xn, it is equal to the probability that xi plus some tau, it is equal to x1, x2 plus tau, it is equal to x2, and so on, xn plus tau, it is equal to xn. For every n and every shift tau, and for all x1, x2, xn from the alphabet set chi. Another definition, it is a discrete stochastic process. X1, x2, and so on is a Markov chain or a Markov process if for n equal to 1, 2, and so on, probability that xn plus 1 it is equal to xn plus 1 given that xn it is equal to xn, xn minus 1 it is equal to xn minus 1, and so on, x1 it is equal to x1, equals the probability that xn plus 1 equal to xn plus 1 given that xn it is equal to xn. For all x1, x2, xn plus 1 from the alphabet set chi. In this case, the joint property mass function of the random variables is given as P of x1, x2, and so on, xn. It is equal to the property of obtaining x1 times the property of obtaining x2 given x1 times the property of obtaining x3 given x2, and so on, property obtaining xn given xn minus 1. To note here, it is that if a discrete stochastic process is a Markov chain, then each random variable depends only on the one preceding it, and it is conditionally independent on all the other preceding random variables. Another definition, it is of the time invariant Markov chain. The Markov chain is called time invariant if the conditional probability P of xn plus 1 given xn does not depend on n. This would mean that the property of xn plus 1 being equal to b, given that xn it is equal to a, it equals probability that x2 it is equal to b, given x1 it is equal to a. And this is for every n equal to 1, 2, and so on, and for every a and b from the alphabet set chi. From that definition to note, it is that if xi is a Markov chain, then xn it is called a state at time n. If the Markov chain it is time invariant, then it is characterized by an initial state, let's say at n equal to 0, and the m times m transition probability matrix, which is such that P of I, j, it is equal to the probability that xn plus 1 it is equal to j, given that xn it is equal to I. And this is for every I and j from the set 1, 2 up to m. If the PMF of a random variable at time n it is P of xn, then the property mass function at time n plus 1 it is given as P of xn plus 1 equals to sum of all xn's, P of xn times the property of the transition from the state xn to the state xn plus 1. Some other definitions include the following. If it is possible to go in the infinite number of steps from any state of the Markov chain to any other state with positive probability, then the Markov chain is called irreducible. Another definition is if the largest common factor of the length of different paths from a state to itself, it is 1, then the Markov chain is called aperiodic. Another one, it is the stationary. If the distribution at the time n plus 1 is the same as the distribution at time n, then that distribution is called stationary. We illustrate all this one with an example. Consider a two-state Markov chain, as it is shown on the figure below, with probability transition matrix P of equal to 1 minus alpha, which gives me the probability of transition from the state 1 to state 1, and alpha, which gives me the probability of the transition from the state 1 to state 2. Beta gives me the probability of transition from the state 2 to the state 1, and 1 minus beta gives me the probability transition from the state 2 to the state 2. We denote with mu, which is a sequence of mu1 and mu2, the stationary distribution, probability distribution, where mu1 and mu2 are the stationary probabilities of the state 1 and the state 2, respectively. We have to determine the stationary probabilities. For this one, we consider the equation that we wrote it before in a matrix form. Mu of n plus 1, it is equal to mu of n times p. P, it is the transition probability, and mu's are the probability distribution. 1, it is mu n plus 1, it is at time n plus 1, and mu n, it is at times n. Since the distribution is stationary, then we can write that mu of n plus 1, it is equal to mu of n, because it does not change. Therefore, we can write this equal to mu, so it does not depend on the index n. Then we can write the equation 1 in this form, mu equal to mu times p. Now we replace the p value that we have it from the previous matrix. Then we obtain these two equations. Mu1, it is equal to 1 minus alpha mu1 plus beta mu2. And mu2, it is equal to alpha mu1 plus 1 minus beta mu2. Or we can rearrange these two equations and get that alpha mu1, it is equal to beta mu2. Now, since mu vector, it is a probability distribution, the mu1 plus mu2 must be equal to 1, normalization condition. Then using also this one as a second equation, then we get that mu1, it is equal to beta over alpha plus beta, and mu2, it is equal to alpha over alpha plus beta. We can furthermore calculate the so-called Shannon entropy of the state xn at time n. And then for this one, we use this equation. H of xn, it is equal to minus sum of the state 1 and 2, mu I log with base 2 of mu I. States are with probability mu1 and mu2. Then we can replace this one, and this sum reduces to minus mu1 log with base 2 mu1 plus mu2 log with base 2 mu2. We replace mu1 and mu2, and we get minus beta over alpha plus beta log with base 2 of beta over alpha plus beta plus alpha over alpha plus beta log with base 2 of alpha over alpha plus beta. Now this gives me the Shannon entropy with this probability distribution. Mu1 and mu2, or alpha over alpha plus beta and beta over alpha plus beta. Next, we'll talk about the entropy rate. By definition, the entropy rate of a stochastic process, xi, is defined as h of some chi equal to the limit where n goes to the infinite of this quantity, 1 over n, and the joint entropy of x1, x2, xn random variables. If this limit exists, of course. Note that for a sequence of n random variables, let's say x1, x2, xn, the entropy rate, h of chi, gives the rate growth of the entropy with increasing n. Consider again this example. A typewriter that has m equally likely output letters. I have to calculate the entropy rate of this one. Now the typewriter, since it has m equally likely output letter, is going to produce, so if I have a sequence of length n, is going to produce m over to the power n sequences of length n. x1, x2, xn, let's say, by picking up randomly n letters out of m. Since each of them is equally likely to occur, then the probability of obtaining one sequence, let's say the sequence x1, x2, xn, denoted as x to the power n, is 1 over m to the power n. Therefore, the joint entropy, it is given like h of x1, x2, xn, it is equal to the minus sum of all sequences x to the power n from the chi to the power n, p of xn, log with base 2 of p of x to the power n. Now p of x to the power n, it is equal to 1 over m to the power n. We replace it on here, then you get minus sum of all x n from the chi n, 1 over m to the power n, log with base 2 of 1 over m to the power n. Now, all these terms do not depend on x to the power n, so I can bring it outside the sum. Then I have in front 1 over m to the power n. Next, I join the minus with log with base 2. Then I get log with base 2 of m to the power n. Then I have the sum of all x n from chi n of 1. But this will give me this sum of ones from all of xn from the chi n. It is all m to the power n. Then m to the power n, m to the power n cancels out. Then you get log with base 2 of m to the power n. Then the entropy rate, by definition, will be obtained as the limit when n goes to the infinite of 1 over n of the joint entropy, which was equal to the log with base 2 of m to the power n. I use the property of the logarithm, and this is equal to the n log with base 2 of m, and n cancels out. Then I obtain just simple log with base 2 of m on the limit when n goes to the infinite, but this does not depend on n, then gives simply log with base 2 of m bits per symbol. Another example, it is the case of independent, identically distributed random variables. Let's say that I have x1, x2, xn, n IID random variables. Now I want to determine the entropy rate of this. Now let's be a sequence of length n, x1, x2, xn. Then the probability of obtaining one realization, let's say x to the power n, which is the sequence little x1, little x2, little xn, it is equal to the p of x to the power n equal to, since these are IID, then it is simply the product of marginals with respect to x1, x2, xn. Furthermore, since the sequence is identically distributed random variables, then each of these marginals, it is equal to the other. So this means that we can say p of x1, it is equal to p of x2, and so on, p of xn. Then p of x to the power n, it is obtained as p of one of these, let's say x1, all this 1 to the power n. Then we can go to calculate the joint entropy, h of x1, x2, xn, then it is equal to, by definition, minus sum of all xn from chi n, p of xn, log with base 2 of p of xn. Now, we can replace p of xn as a product, p of x1, p of x2, p of xn. The same, we also do it inside the log with base 2. Then log with base 2 of the product of P of x1 times P of x2 and so on, P of xn, it is equal to the sum of I from 1 to n, log with base 2 of P of xi. Then we obtain the third line. Then we swap the position of the sum. We've put on the fourth line first the sum of I from 1 to n, and secondly, the sum of xn from chi to the power n. Then we have P of x1, P of x2 up to P of xn, log with base 2 of P of xi. Now, on the fourth term, we can notice that this P of sum of all xn from chi to the power n, it is actually n sums from x1, x2, and so on, xn. Now, what we do, we can notice that the log with base 2 of P of xi, right, depend only on the xi's. It does not depend on x1 up to xi minus 1 or xi plus 1 up to xn. So what I do, the second sum, it is split on two sums. One for from x1, xi minus 1, xi plus 1 up to xn, and the other one simply the sum of xi from chi. Now, the first sum, if I sum over all x1 up to xi minus 1 and xi plus 1 up to xn, all these joint property mass function, then this will give me the marginal with respect to xi based on the property and statistics. Then I'm left from the term before the log with base 2, just P of xi. Then log with base 2 of P of xi as it is. Then I obtain the last line. Now on the last line, minus sign in front, with sum of all xi's from chi, P of xi log with base 2 of P of xi gives me simply the entropy of the x1 random variable, right, or one of these. Then, right, then I have minus sum of I from 1 to n h of xi. Since all these random variables are IID, then all P of xi's are the same. So also the h of xi's. Then I could say that the sum of I from 1 to n h of xi, it is simply n entropy of the one of the random variable, let's say x1. Then I get n h of x1. Then entropy rate, it is simply the limit when n goes to the infinite of 1 over n joint entropy. Joint entropy is equal to n h of x1, and n cancels out. Then I obtain, for the same reason as before, h of x1 bits per symbol. Now we remove this identical from the IID. Then we have considered the case when x1, x2, xn are simply n independent distributed random variables. But to determine the entropy rate in this case, again, we consider sequence of length n, x1, x2, xn, with property obtaining one of the realizations, let's say the sequence little x1, x2, xn, given as below. P of xn, it is equal to P of x1 times P of x2, and so on, P of xn. This is because still the random variables are independent. Then we can use the same reasons as before, all right, to obtain the joint entropy. So I'm not going to explain the line from 1 to the 4th because are similar, but we can stop at the last line, minus sum of I from 1 to n, sum of all xi's from chi, P of xi log with base 2 of P of xi. Now, the second sum with minus in front gives me the entropy h of xi random variable. Then I obtain sum of I from 1 to n, h of xi. Now you could notice, since the random variables x1, xn are not identical, then they don't have the same probability distribution. So this means that they don't have the same Shannon entropy. Then h of xi's are not equal. That this means that this sum cannot be factorized as n h of x1 as before. And this is the only difference with what we explained before. This is why we did fast this slide. So the entropy rate, then, it is simply limit when n goes to infinite of 1 over n joint entropy, then the limit when n goes to the infinite of 1 over n sum of I from 1 to n h of x I. Right? Note that h of xi's are not equal. And so there exists a sequence x1, x2, xn such that the limit 1 over n sum of I from 1 to n h of xi may also not exist at all. All right, so this is something, the difference with a case of identical independent random variables. Now we'll give another distribution or another definition of the so-called entropy rate. By definition, the entropy rate of a stochastic process xi can also be defined by this quantity. We denote this for the moment h prime to distinguish that from the previous one. But we are going to prove that these are identical definitions. So we denoted h prime of chi equal to the limit when n goes to the infinite, h of xn given xn minus 1, xn minus 2, x1. If this limit exists, note that S will be shown in the following entropy rate given by equation 4 before, and this one that given by equation 5 are actually the same, identical. So this means that h of chi is equal to actually h prime of chi, although they are determined in terms of different related quantities. Right? Now, before we go to this thing to prove that these two definitions are identical, we are going to give some definitions. First, we go to the Cesaro mean. Now, the theorem says like this: if an converges to some a, and bn is equal to 1 over n sum of I from 1 to n ai, then bn converges to a2. Now, this is a simple proof, all right? There is an informal proof of the theorem as follows. Since an converges to a, then bn, which is equal to 1 over n sum of I from 1 to n ai, converges to 1 over n sum of I from 1 to n of a. Now, since a does not depend on the index I, then I'll have a times sum of I from 1 to n a gives me n times a. N times a divided by n, and n cancels out, give me simple a, which is the proof of the theorem. Now we are going to prove some important theorems. For a stationary stochastic process, entropy of xn given xn minus 1 and so on x1 is non-increasing in n, and as a limit h prime of chi. So the entropy rate based on the second definition. Now, using the fact that the conditioning reduces the entropy, a theorem that we showed last week, this would mean that the condition entropy of xn plus 1 given x1, x2, xn, it is less equal to the condition entropy of xn plus 1 given x2 and so on xn. So I remove the conditioning from x1. Then this increases the uncertainty. Since the process is stationary, then the condition entropy of xn plus 1 given x2 and so on xn, it is also equal to, we do a shift by 1. Then I will have n plus 1 minus 1 gives me xn given, if I do it, so I've jumped one step, x2 minus 1 gives you x1, and so on, xn, the last one, minus 1 gives xn minus 1. Then I rearranged, I reordered the terms after the conditioning as starting from the last one, xn minus 1, xn minus 2, and ending at x1. So this is simply a rearrangement. Therefore, if I use the equation 1 and 2, I obtain that condition entropy of xn plus 1, condition on xn minus 1 up to x1, it is less equal to condition entropy of xn on xn minus 1, xn minus 2, x1. And this is what we wanted to show, that because this shows that the condition entropy of xn given xn minus 1, xn minus 2, x1, it is non-increasing sequence of non-negative numbers. All right? Non-increasing because I have less equidon here, and non-negative numbers because the entropies, condition entropies are non-negative. All right. Now you could notice that this also has the limit h prime. All right. Why? Because by definition of h prime that we gave it on the previous slide. Now the most important theorem for a stationary stochastic process, the limits on the equation 4 and 5 given on the previous slides exist and they are equal. So this would mean that the entropy rate chi, h of chi, it is equal to the entropy rate definition h prime of chi. How to prove this one? Using the chain rule of the entropy. The joint entropy, h of x1, x2, xn, it is equal to the sum of I from 1 to n, condition entropy of xi given xi minus 1, xi minus 2, x1, right? Dividing both sides of this equation by n, we get this one, 1 over n, joint entropy equal to 1 over n, sum of I from 1 to n, conditional entropies. Then next take the limit when n goes to the infinite of the both sides. Then we get the left-hand side give me the h of chi, the first definition of the entropy. And the second, the right-hand side, it is the limit of n going to infinite, 1 over n, sum of I from 1 to n, condition entropy of xi given xi minus 1, xi minus 2, x1. Right? Now this is equal to the limit when n goes to the infinite of the h of xn given xn minus 1, xn minus 2, x1. But this, by definition, it is what? It is the so-called h prime of chi, all right? Which is the proof of the theorem. Now we can say some other consequences of the previous theorem. For a stationary Markov chain, we have that condition entropy of xn given xn minus 1 and so on, xn minus 2, x1. It is also equal to the condition entropy of xn on xn minus 1. Or furthermore, it is equal to the entropy of x2 given x1. Taking the limit when n goes to infinite of the both sides. Now on the left-hand side gives me the entropy rate, h of chi or h of prime of chi, which is equal to the limit when n goes to the infinite of h of xn given xn minus 1, xn minus 2, and so on, x1. Now, furthermore, this is equal to the limit when n goes to the infinite of h of xn given xn minus 1, or it is equal to the limit when n goes to the infinite h of x2 given x1, but this does not depend on n. Then I can remove the limit, then I have h of x2 given x1. Here, the condition entropy is calculated using the probability distribution mu, which is the solution of this equation, mu equal to mu times p. Now comes another theorem. Let xi be a stationary Markov chain with stationary distribution mu and transition matrix p. Let x1 as a probability distribution in mu, then the entropy rate, it is as the following. H of chi, it is equal to the minus sum of I, sum of j, mu I, p of ij, log with base 2 of p of ij. Right? Now, starting with a relation mu of chi equal to mu of x2 given x1, then we get the following. By the way, on the definition, when I say x1 as the probability distribution in mu, x1 could be any of these xi's, all right? Then we have the entropy rate. So I'm continue now. Entropy rate h of chi, it is equal to h of x2 given x1, then sum of all x1s, all right? So x1, it is just as a picked one, all right? One of them. then P of x1, H of x2 given x1 equal to x1, and this is equal to sum of all x1s, P of x1 multiplies minus, I'm replacing H of x2 given x1 equal to x1, which is equal to minus sum of all x2s, P of x2 given x1, log with base 2 of P of x2 given x1. Then this is equal to minus sum of all i's, sum of all j's. P of x1 is placed with mu I. P of x2 given x1 gives me P of ij. Then I have log with base 2. And another time I replace P of x2 given x1 as P of ij. Then I obtain the equation 7 that I wanted to show. Now consider again the exercise that we showed before of the two-state Markov chain with a property transition matrix P, 1 minus alpha, alpha, beta, 1 minus beta. For alpha, transition from state 1 to state 2, beta, transition from state 2 to state 1, 1 minus alpha, transition from state 1 to state 1, and 1 minus beta, transition from state 2 to state 2. Again, we denote with mu the stationary property distribution vector with components mu1 and mu2, which are stationary probabilities at the state 1 and state 2 respective. Then I want to determine the entropy rate of this process. Now, based on the definition, since the is a stationary Markov chain, based on the previous theorem, entropy rate, it is equal to the condition entropy of x2 given x1. Or it is equal to the minus sum of all i's, sum of all j's, mu I, P of ij, log with base 2 of P of ij. Then we get the entropy rate, which is equal to the condition entropy of x2 given x1. It is equal to minus, since I have two states, then this sum reduces to minus mu 1. So for I equal to 1, I have mu 1. Then I have P of 1, 1 log with base 2 of P of 1, 1 plus P of 1, 2 log with base 2 of P of 1, 2 minus, now I equal to 2, then I get mu 2 times P to 1 log with base 2 of P to 1 plus P to 2 log with base 2 of P to 2. Now I replace mu 1 and mu 2 based on the previous exercise. Then I get minus beta over alpha plus beta for mu 1. Then I have P of 1, 1 minus alpha log with base 2 of 1 minus alpha. P of 1 to alpha, then I have alpha log with base 2 of alpha. Then minus alpha over alpha plus beta for mu 2. Then I get beta log with base 2 of beta for P to 1 beta. Then plus 1 minus beta for P to 2 log with base 2 of 1 minus beta. Then this would give me the first term. If I take the minus and join with the terms on the parentheses, then this will give me H with probability distribution alpha. Then I get the factor beta over alpha plus beta, plus the second term, it is alpha over alpha plus beta, and minus with the term on the parentheses gives me the entropy with probability distribution beta. Now consider another exercise. Consider the stochastic process representing a random walk in a weighted undirected graph with m nodes. Let's say 1, 2, up to m. Let mu ij be a positive, right, greater than 0, and are the weights of the wedge joining two nodes, let's say node I and node j. And they are such that mu ij it is equal to mu ji, and mu ij it is equal to 0 if there is no edge between the nodes I and j. We denote with xn a stochastic process where xn takes the value 1, 2, and so on m. And this is the sequence of nodes visited by a particle or a walker, all right, a random walker, a particle, performing a random walk on the graph. I want to calculate the entropy rate of this process. This graph, it is just for illustration. Now we denote with Pij the transition probability from the node I to the node J, defined as the following: mu ij over sum of all k's mu I k. All right. Now assume that we have a stationary Markov chain distribution. The property being at the node I, it is given as mu I equal to mu I over 2 mu, where the mu is the total weight of the edges emanating from the node I. Then W, it is equal to the sum of all I and j's such that j it is greater than I, mu ij. And mu I it is equal to the sum of all j's, wij's. Now, this can be verified since the stationary Markov chain distribution has to satisfy the relation mu equal to mu times p. Now, you could show this one using this sum of all i's mu I pij. It is sum of all i's wi over 2w for mu I. Then I have for pij mu I wij over wi. Then this is equal to sum of all i's 1 over 2w times wij, because wi cancels out. 1 over 2w does not depend on I can bring it outside. Then the sum of all i's wij gives me simply wj. Then I get wj over 2w, or it is equal to mu j. Now we can calculate entropy rate as the condition entropy of x2 given x1. And this is shown on the next slide. Our entropy rate, it is equal to the minus sum of all i's mu I, sum of all j's, pij, log base 2 of pij. Now, this is equal to minus sum of all i's. I replace for mu I, wi over 2w. Sum of all j's, wij over wi. Log base 2 of wij over wi. Now, this is equal to, I group together the sums, minus sum of all i's, sum of all j's, wij over 2w, because wi cancels out, log base 2 of wij over wi. Now what I do on the term inside the logarithm with base 2, I multiply and divide by 2 times w and remain the same. Then what I do, I split it. I group together wij with 2w and 2w with wi. Then I will obtain two sums. Sum on the first term, which is minus sum of all I, sum of all j's, wij over 2w, log base 2 of wij over 2w, plus, because this log, I take the log of the inverse, then this minus becomes plus. Then I have wi, wj, wij over 2w, log base 2. Then I have instead wi over 2w, the inverse. Now you could notice that the first term gives me the Shannon entropy with probability distribution wij over 2w. Then the second term with minus in front gives me the Shannon entropy, but with probability distribution wi over 2w. The reason is because if you take the sum on the second term over j of wij, this will give wi. Then I will be left with one sum, wi, all right, sum of all i's, wi over 2w, log base 2 of wi over 2w. And this gives me the Shannon entropy with probability distribution wi over 2w. Now, we consider the special case where all edges have equal weights. So this means that all wi's are the same. This would mean, and we denoted this one as ei. And this is a sum of all j, wij. Now this gives me the number of edges going out of the node I. and 2 times E, or which is equal to 2W, it is equal to the sum of all i's EI, right? Now this gives the total number of edges in the graph summed over each node. By the way, we didn't say it before, but this 2 in front comes because when you sum over all nodes I remember this is undirected graph. So if the node I has an edge with node J, when we run the sum over all i's and we go to the node J, then we count the same EI, which now goes from J to I. So this is the same as saying we counted twice the same edge. And this is why these 2 comes in front, all right? Now the stationary distribution, it is equal to the mu I equal to EI over 2E. And the transition probability, it is equal to Pij equal to Wij over sum of all k's Wik, which is equal to 1 over EI. Now the entropy rate in that case, it is equal to, again, the sum of minus sum of all i's mu I, sum of all j's Pij log base 2 of Pij. Then I replace mu I with EI over 2E, and I replace Pij with 1 over EI. Then I obtain, for the same reason, all right, here, the first term, it is equal to, first sum, it is equal to sum of all minus sum of all i's EI over 2E, log with base 2 of 1 over EI, all right? Because EI here, EI cancels out, all right? Then I obtain equal to, I do the same trick, I multiply by 2E and divide by 2E, all right, on here, on this, on here. Then I get equal to sum of all minus sum of all i's, EI over 2E, log with base 2, 2E over 2E times EI, right? Now I can write this log with base 2 of 2E over 2E times EI as 2 sums, 1 over, as a product 1 over 2E. Then I obtain the first term, log with base 2 of 1 over 2E. Then I have left with 2E over EI, log with base 2 of that. I take the inverse of this, log with base 2 of EI over 2E. Then I obtain this one, but the inverse will bring me a minus, minus, minus gives me a plus. And then I can see the first one, all right? The first sum here gives me, you could simplify this one. This will give you log with base 2 of 1 over 2E gives minus log with base 2 of 2E. I can bring it outside the sum. Then moreover, 1 over 2E, I can bring it outside the sum. But the sum of all i's, EI, gives me 2E. 2E over 2E cancels out, and I'm left with log with base 2 of 2E on the first term. Then the second term with a minus in front gives me the entropy, Shannon entropy, with this probability distribution, E1 over 2E, E2 over 2E, and so on, EM over 2E. Now, next, I'm going to talk about the second law of thermodynamics and how this connects to the information theory that we have discussed so far. Now, we give first the physics point of view. From the physics point of view, the second law of thermodynamics states the following. As it is a postulate, the entropy function S of the internal energy E and the mechanical extensive parameters X vector is a monotonically increasing function of E, and if the state B is reached adiabatically from the state A, then S of B, it is greater or equal to S of A, right? Now, in statistical thermodynamics, the entropy, which is given by the Boltzmann's entropy, is defined from the week 1 as S equal to KB ln of omega, where omega it is the number of macrostates. Then we show that for a stationary probability distribution, also this we showed on the first week, mu I it is equal to 1 over omega. Then we get that S it is equal to minus KB sum of all i's mu I ln of mu I. And we said that this is exactly the Shannon entropy up to some factor. Now, the next question that we want to answer, it is, let's see why does the entropy increase? Now, for this one, we go back to the definition of the relative entropy. And we show that the relative entropy, it decreases. For that, consider a Markov chain, discrete time process. Let's say x1, x2, xn, where n, it is the discrete time. Then we consider mu and mu prime, two probability distribution, mu n, mu prime n at time n, and mu n plus 1, mu prime n plus 1 at some time, later time n plus 1. We consider P the transition matrix from the state xn to the xn plus 1. And it is given as the conditional probability, we denote it by R, of xn plus 1 given xn. Then the joint property mass function, P of xn and xn plus 1 and Q of xn plus 1 are defined based on the probability and statistics as P of xn times condition probability, xn plus 1 given xn, and Q of xn and xn plus 1, it is defined as Q of xn times R of xn plus 1 given xn. Using the chain rule of the relative entropy, we have shown this before, then the relative entropy of the joint probability mass functions, P from Q, it is equal to the relative entropy of the marginal probability distribution, P from Q, plus relative entropy of the conditional probabilities, P of xn plus 1 given xn from Q of xn plus 1 given xn. Moreover, this is equal to, since the process here, it is a Markov chain, that this is equal to, all right, to the, does not depend on the index n, it is equal to the relative entropy of the P of xn plus 1 from Q of xn plus 1 plus relative entropy P of xn given xn plus 1 from Q of xn given xn plus 1. This could be also called a time reversible property. So this means that as equal chances, a state, Walker, as equal chances being, if it is at state n going to n plus 1, as equal chances to go back from n plus 1 to the state n. So this is something that we can assume. This is also called, in another terminology for this is called detailed balance condition in some other fields, all right, for the Markov chain. Now, since P and Q are derived from the same Markov chain, then we can say that the condition probability P of xn plus 1 given xn, it is equal to the Q of xn plus 1 given xn, and it is equal to R of xn plus 1 given xn, which implies, all right, that relative entropy of the condition probabilities, it is equal to 0, because P it is equal to Q. This indicates that using also the non-negativity of relative entropy, which means that D of P of xn given xn plus 1 from Q of xn given xn plus 1, it is greater or equal to 0. This implies that relative entropy of P of xn from Q of xn, it is greater or equal to the relative entropy of P of xn plus 1 from Q of xn plus 1. This result indicates that the distance between the property mass function is decreasing with time n. for a Markov chain. How you could practically interpret this one? This would be as consequences in different fields. One of these could be on economics, right? For example, consider the tax system for the redistribution of the wealth when compared between two countries. If P of xn and Q of xn represent the distribution of the wealth among the people in the two countries, then the inequality D of P of xn from Q of xn greater or equal to D of P of xn plus 1 from Q of xn plus 1 implies that the relative entropy distance between the two distributions decreases with time. That is, the wealth distribution becomes more similar with time n. So this would mean that if one country copies the tax system of another country, this would mean with time the wealth distribution among the people from the both countries should be similar if this reform, tax system reform, is applied correctly, and if we include all the dependencies inside. All right, so this is something that this means in the more simple terms. Now we go back to our original problem. We consider now the relative entropy or some probability distribution from the stationary distribution U. Again, the relative entropy D of P from U between distribution P of xn on the state at time n and the stationary distribution U decreases with n. Yes. So using the result of the previous slide, this would mean that D of P of xn from Q of xn, it is greater or equal to the P of xn plus 1, Q of xn plus 1. Consider Q as U. Since this is a stationary distribution, does not depend on the index n, this would mean that Q of xn plus 1, it is equal to Q of xn, it is equal to U. Then this would mean that D of P of xn from U, it is greater or equal to D of P of xn plus 1 from U. That indicates that the state distribution gets closer to the stationary distribution U with time n. Or D of P from U is a monotonically non-increasing, non-negative sequence. However, there is a remark, the fact that the relative entropy decreases does not imply that the entropy increases. In fact, that will be true only if the stationary distribution is, moreover, a uniform distribution, as we'll show in the next slide. Now, before I go there, consider this one, the relative entropy, D of P of xn from U, between a distribution P of xn on the state at time n, and the stationary distribution U and the uniform increases with n. Let's show this one. Using the result from the previous weeks, if you remember, if U now is a stationary but also uniform, then I have proved the theorem before that the relative entropy of P from U, it is equal to the log with base 2 of the cardinality chi of the x random variable minus entropy or with proper distribution P of xn. Now I could further write log with base 2 of cardinality of chi minus h of xn random variable. Now, moreover, I know, all right, that since if I say that the entropy increases, then this would be greater or equal to log with base 2 of cardinality of chi minus entropy at x n plus 1. If I assume now, all right, from this one, you could assume, you could get that h of xn, it is less equal to h of xn plus 1. That indicates that the entropy increases with time. Is it clear? On this one, on the last one, I've used the fact that the relative entropy decreases in time, the what that we showed. All right, from the D of P of xn from U to the greater or equal to the log with base 2 of chi minus h of xn plus 1, I use the fact that the relative entropy decreases on time. All right. However, from the second line to the third line to jump, all right, this is the same as saying that the h of xn it is less equal to the h of xn plus 1, which is what I wanted to show. Now let's give some other definition: a double stochastic process. By definition, a property transition matrix P with P of ij equal to property of xn plus 1 being equal to j and xn given xn equal to y is called doubly stochastic if sum of all i's P of ij is equal to 1 for j equal to 1, 2, and so on. Similarly, also sum of all j's P of ij is equal to 1 for I equal to 1, 2, and so on. This is the same as saying if you sum along the rows, you get 1, and if you sum along each column, you get 1 again. The uniform distribution is a stationary distribution of P if and only if the property transition matrix P is a doubly stochastic. Now, as a corollary about the conditional entropy of xn given x1 increases with n for a stationary Markov process. To prove this one, if the Markov process is stationary, this would mean then the entropy of xn it is constant, and so the entropy it is non-increasing. On the other hand, the condition entropy h of xn given x1 increases with n. That is, the condition uncertainty on the future increases. For that, the condition entropy of xn given x1 it is greatly equal to the h of xn given x1 and x2. This is because of the theorem of last week, condition reduces entropy. Now, because the fact it is a Markov chain, then I could say that depends, it is equal to the entropy of xn given x2. And because it is a stationary process, then it is equal to the entropy of xn minus 1 given x1. So I shift it with 1 in time. Now, another theorem, which is accepted without a proof here, it is the shuffling. Consider x is a random variable from chi set x1, x2, xn. If t is a shuffle, so any function, shuffle, for example, permutation of the indices could be a shuffling of the set chi, which is independent on x, then the entropy of the shuffled sequence increases. So it is greater or equal to h of x. Now, some functions of Markov chains. Consider x1, x2, xn a stationary Markov chain. Consider also y1, y2, and yn from epsilon be a random process with states defined as a function of the corresponding state in the Markov chain. So this means that yi's are equal to f of xi's. Then the entropy rate of y, which is defined as h of epsilon, the limit of n goes to infinite, condition entropy, yn given yn minus 1, yn minus 2, y1. Then this is the limit from the above. All right. It is given as entropy of yn given a yn minus 1, yn minus 2, y1. It is greater or equal to the entropy rate, which is practically very slow to reach as a limit. Now the lemma shows that entropy of yn given yn minus 1, yn minus 2, y2, x1, it is less equal to the entropy rate of epsilon. Now to show this one, for k equal to 1, 2, and so on, we have the following. So the h of yn given yn minus 1, yn minus 2, y2, x1, it is equal to the entropy, if we assume that y1 it is equal to f of x1, then you have h of yn given yn minus 1 and so on y2, y1, and x1. This is, we have said this one, this is because of the Markov chain that we have shown on the last week. All right? Now, again, based on the Markovity, we can write that h of yn given yn minus 1 and so on y1, and x1, x0, x minus 1 and so on x minus k. Then because y equal to f of xi, we can write that y, h of yn given yn minus 1 and so on y1, x1, x0, x minus 1 and so on x minus k, y0, y minus 1 and so on y minus k. Then condition reduces the entropy, will give me the third equation less equal to the fourth one, h of yn given yn minus 1, y1, y0, y minus 1, y minus k. So I remove the condition from the x1, x0 up to x minus k here. Then because of the stationarity, I do a shift on time, then I'll get h of yn plus k plus 1 given yn plus k and so on y1, right? Now, since the inequality is true for every k, it is true also in the limit of k. So this means that h of yn given yn minus 1, yn minus 2, y1 and x1, it is less equal to the limit when k goes to infinite of h of yn plus k plus 1 given a yn plus k up to y1, which is equal to the entropy rate, what I wanted to show. Now, a lemma comes from this one, show that h of yn given yn minus 1, yn minus 2, y1, minus h of yn given yn minus 1, y1, x1 converges to 0. Now, this can be also shown by definition of the condition mutual information. We have that the difference between the h of yn given yn minus 1, yn minus 2, y1 minus h of yn given yn minus 1 and so on y1, x1, it is equal to the condition mutual information between x1 and yn given yn minus 1 up to y1. Then the mutual information between x1 and all the random variables y1 up to yn increases with n. Then this would mean then the mutual information between x1 and all y1, y2, yn, it is less equal to the h of x1. If you take the limit when n goes to the infinite of the both sides, the right-hand side does not depend on n, gives you h of x1. Then on the left-hand side, I obtain the limit when n goes to the infinite of the mutual information between x1 and random variables y1 to yn. Then using the chain rule for the mutual information, we'll obtain that h of x is greater or equal to the limit when n goes to the infinite, the mutual information between x1 and all y1 random variables, y1 to yn. And this is the right-hand side, it is equal to the limit when n goes to the infinite, sum of I from 1 to n. I have used the chain rule of the mutual information, I of mutual information between x1 and y1 given y of I minus 1 up to y1. Then this is equal to take the limit when n goes to the infinite, then the upper limit of the sum goes to the infinite. Then I have sum of I from 1 to infinite, I condition mutual information between x1 and y1 given yi minus 1 up to y1. Since each term in the sum is non-negative and the sum is bound, then the limit when n goes to the infinite of this conditional mutual information between x1 and y1 given y of n minus 1 up to y1, it is equal to 0. Now, this is a definition of the Eden-Markov model. Combining the two lemmas, we have that the condition entropy of yn given yn minus 1 up to y1 and x1, it is less equal to the entropy rate h of epsilon, and it is less equal to the condition entropy of yn given yn minus 1 up to y1. This is using the previous two lemmas, but also the fact that the condition reduces the entropy. Consider a Markov process, x1, x2, xn, and the new process, y1, y2, yn, where y1 is drawn from with probability p of yi given xi, then yi is the condition independent of all other indexes xj for j different from I. Then you could write that the joint property of the sequence is xn yn. It is equal to the p of x1 times product of I from 1 to n minus 1, p of xi plus 1 given xi times product of I from 1 to n, p of yi given xi. This process, if this is condition satisfied, is called either Markov model. As a summary of the presentation, you should know about the Markov chains and their properties. You should know about the entropy rate, how to calculate the entropy rate on the examples. You should know about the relationship with the second law of thermodynamics. Thank you for your attention and some references for you. We have given also before this one. All right, thank you. See you next time.